So everything is done on a reference element and then transported to the real element using geometric transformation, which can be itself high order. Right. A small comment regarding the particular point set, which is the so-called FEniCS point set. I display them here. Well, it's not really the FEniCS point set, but the Warblend point set. But they are very similar. If you plot them, they are going to be very similar. It's just that I didn't have the graphic when I did the slides. And here, what you see is basically the growth as n increases of the stiffness matrix when you use either Lagrange polynomials built at equidistributed point set, Warblend, and FEniCS. And here the slope here is n to the fourth, right? So we recover the n to the fourth growth for the FEniCS point set, which is a feature of this family. And you see that for the equidistributed that it blows up relatively rapidly. The FEniCS point set is basically a set of points which maximize the determinant of the van der Waals matrix, of generalized van der Waals matrix. And it allows you afterwards to have a Lebesgue constant which is bounded. So whenever I talk about higher order finite elements, a Lagrange finite element, then we use FEniCS point sets. So regarding the mesh data structure, so basically we have, we handle different kind of convexes, and with associated geometric transformations that can be high order. And one particular library that we use of Boost is called the Boost multi-index library. This is extremely convenient because it allows you to view your data structure using many different iterators. If you look at the current finite element libraries, say for example libmesh, then you would see all kind of iterators over the mesh data structures, right? And I think it's quite tough to implement all of them and to maintain them. And here I find out that the Boost multi-index library allow you to write in a very concise way your mesh data structures. For example, it will allow you to provide iterators over all the elements of your mesh, over marked elements, a marker being an integer, marked elements of your mesh, over the internal elements of your mesh, over faces that are in between processes in a parallel setting. So it's with this library you can write very rapidly very complex data structure, and you can then view this go through the data structure in a very easy way. Regarding the parallel strategy, we do element-wise partitioning. We use Scotch or Metis, or there is a Metis interface to Scotch. And whenever you write, if you are in a parallel environment, basically, when you iterate over the elements, for example, of the mesh, if you are in a parallel environment, that would be only the elements of the current processor, right? Idem for the other ones. Now we have the function spaces. So basically the data structure, which is called function space, it is parameterized by the mesh and basis function, but it allows to write product of n function spaces, a mix of scalar, vectorial, matricial function space. And you can of course extract each function associated subfunction space and the associated component spaces if needed, if it applies. So here is an example. For example, here you have, let's say, the first space, the basis functions which be Lagrange of order 2, and vectorial, and the second one Lagrange of order 1 and scalar. And then you just instantiate your space here. You can extract the subspace like this, define an element of XX like this. The element of a space is a subclass of the space. The nice feature here is that with this type of programming, this is very difficult for the programmer to do mistakes, because this is strongly typed, right? If you don't have the same, if you want to equate two functions but of different spaces, then you won't be able to do it that easily using this. You will have to go through the algebraic representation in order to do that, right? But at the level of a function, you are forbidden you are forbidden to do many wrong things. And what you can do also is extract sub-functions, like for example the second one, a function which is associated with the second function space. So here that would be P is an element, is a view on the function associated with the second space. A more complicated example here. This is just a snippet of one of our tutorial example. It's a coupling between heat transfer and fluid flow in a closed square domain. Basically, it's natural convection. So you heat up on one side and you look at the fluid flow inside the box. The thing is that since you don't control the pressure on the boundary, you will know the pressure up to a constant, and eventually that will pose a problem. So what we do here is that we add Lagrange multipliers, which are basically the constants, and we impose that the average pressure, the mean pressure, is set to 0. So we add an extra equation in order to deal with the pressure being known to a constant. We set the mean pressure to 0. And in order to do that, so we have the space for the velocity, or the basis function for the velocity, the pressure, the temperature, and we have an extra space for the Lagrange multiplier, which are basically constant function over the whole domain. So you can do that. If you want to have P0 functions, you would need to add discontinuous here. These are constant function over the whole domain. And then our function space would be, so we set the basis function here, and the function space reads like that. And then you go on with the definition of your problem. Then we have the operators and forms. So basically we can deal with either full or blockwise matrix vector assembly. And we have typically high order concept like operators, linear operators, functionals, like linear functionals. So for example, this is a linear operator between a space x1 and x2 of type x1 and x2. So we have the space, we instantiate the spaces, we define elements of the spaces, then we instantiate the associated operator, we define the operator here. This is a linear operator, so the algebraic representation will be a matrix, right? And then when you apply the operator to a function of x1, then what you retrieve is basically an element of the dual space of the image here. So that would be a linear functional here from x2 to r, which we name f. Then we get f, and then eventually, if we have v in x2, then we can apply f on v and get a real, right? And finally, in order to be able to write this kind of thing, the last main ingredient of the domain-specific language is well, it's the language itself, or the language for the expression, the integral and projections. So basically, it's heavy use of meta and functional programming. So the MPL, the meta programming library, is used heavily with high-order function. I think I push this library to the limit. Another one which is very important, because once you have your abstract data type, what you would like to have is to be able to associate it with runtime data structure. And for this you need the Boost Fusion library to make the link between compile time structure and runtime structure. So I use that also a lot. And regarding the language, what is very important is that it uses lazy evaluation. So there is a decoupling between constructing the expression tree at compile time and evaluating the expression tree.